Hello everyone, this is the solution video to Lab Exam 1. Now here the question was to basically re-implement the root locus gain condition and angle condition so that it helps us out in determining if a certain pole with a certain transfer function with numerator and denominator coefficients given here is on the root locus plot or not, and if it is, what is theta and which gain does that. So basically this is the question that we have, and I have created a main script where I have basically the example here, the example inputs defined, and then we have also the function itself. Now the restriction was to only use MATLAB's vectorized functions because we don't really need anything else. So let's start with the poles and zeros because we need poles and zeros in this case. And we can use basically the roots function, which uses a vector in order to determine the roots of that corresponding vector. So these are going to be the zeros. And then we also have the poles for by using the denominator here. Now what we need is, at this point, we need to draw some vectors from the open loop poles to the destination point, which is pole in this case, and also from the open loop zeros to this destination pole in order to calculate basically their angles and stuff. So before I move on, I'm just going to copy these output arguments here down here and set them to, let's say, false, theta equals 0, and stuff like that, so that even if I mess up something, I shouldn't mess up the script here. So let's see zeros and cpoles. So if you don't do this, where is it? Here we go. Let me just change places. Okay. So if we run main, there we go. We have basically our poles, but we don't have any zeros, so therefore we don't have zeros. It's an empty vector. And then we have all the other stuff. If I, for example, comment out something here, you will see that immediately some output argument errors will occur, and you can see any possible others are not assigned. So please avoid that. Even if it's not correct, just define some certain outputs so that it runs and doesn't crash, because my script will definitely look for these output arguments because it's going to test them. So yeah. Now when we have the poles, we need to have the distance vectors to the design point, and I can just use pole minus in this case in order to create these vectors. Now if you pay attention, you can see that these are not the poles anymore. These are basically the distance vectors, and we don't have any for the zeros here. So what I'm then interested in is basically theta and how I can calculate that. And it's quite easy if you think about it. We will use some tan function in order to convert the imaginary part divided by the real part into some angle data here. I would rather use tan 2 in order to convert them into angle because it uses a 4 quadrants inverse, whereas the tan itself is between minus pi and pi as far as I remember. Because we have asymptotes for tan, this kind of gets rid of the unnecessary conversions. And then we take the imaginary part of the poles, comma, the real parts of the poles, not the ratio. This one works different because it needs each individual sign in order to calculate in which quadrant this is. So I'm basically going to take these and see what the result is going to be. And yeah, we can see that these are the angles. Now the problem with this is that this is in radians and I like to work in degrees. You can then use D here and we end up in this here. So I'm going to basically need to take the sum of this vector, because the sum of the angles of the poles, or from the poles to the destination point, minus the same for the zeros. So we have this nice handy vectorized function, which is called sum, which will take the sum over a vector. And then minus, and then the same here, but for the zeros. Even if we don't have them, I'm just going to write them down here. So now it looks different. and theta is basically going to be 0. Of course, I can get rid of this part here, and yeah, this is basically theta here, and we've calculated it. There we go. Of course, this theta is going to be converted into the result variable, which I'm going to do now. And it's quite important, and as far as I remember, I have talked about this in the explanation video. We need to round this value here so that we don't actually be too strict to it. So if we use round, this is going to be 1 decimal. So we just want to have around 0 here. I can just show you how this works. 1.2345, it will just return 1. And if this is basically 1.5, it will return 2. So it kind of does the expected thing here. I'm going to round this theta because that's going to be relevant. And then I need the mod operator here in order to see if it's equal to 180 degrees, equal to 0, equal to 360. So that's going to be calculated by that. So this part is important because we wanted this to be a little bit more extensive than just having equals 0. So in this case, we seem to be just on the right track. Now, the important thing here is that if we are going to calculate k, we can just use result internally in order to check if we are going to calculate it or not. So that's going to be basically the implementation here. And here we are going to look for the result. And if it's true, then we satisfy the angle condition. Now we should basically state the gain condition. Now the gain condition is also similar to this, where we again use something about the poles. We will take the real part of the poles, for example, take the dot operator here. So this is another vectorized function here, which will take individual squares. And then we will have the imaginary part of the poles. And then the whole thing square rooted is going to be the thing that we need at this point. Now, at these square roots, what I'm basically doing is I'm just looking for the absolute value of the distance. You can also use the absolute value, no big deal, but I wanted to show you in its bare minimum form. So I'm going to do this, and I'm going to multiply all the elements of this because we have multiple vectors. We are going to use another vectorized function, which is called product, which will calculate the product of each individual element in the vector here. So I'm going to divide this into the product of zeros because that's the rule, that's the condition here, and that should be basically it. But still, there's a slight issue here, and that's going to be about theta itself. Because theta determines if it's on the root locus or not, we didn't really pay attention if it's on the positive root locus or if it's on the negative root locus plot. So therefore, if we have theta equals 0 or a greater value than 0, then it kind of depends. If it's 0, it will be on the negative root locus because the minus sign will contribute 180 degrees. Or if it's 180 degrees, it will be on the positive root locus. So that will change the sign of our k. Even if we don't change the way of calculating the gain, this sign will change. So being lazy, I'm just going to say if theta is bigger than 0, I'm assuming that this should be 180 degrees. And otherwise, it's going to be basically the negative root locus here. So the first one is the positive root locus. Here, I'm just going to add a negative sign in order to fix the whole thing here. So this should be basically it. And let's test this out. When we run the script, we get -2. And if we define the transfer function, if result, we can again use this if result here. If it is on the root locus, maybe this doesn't really depend on that, but num, then that's going to be the transfer function that we're looking at. But then the feedback or the closed loop feedback calculation is going to be here, k times cs, 1. And I can just look at the ZPK form, and let me also print the pole again in order to see if it's on the root locus or not. And you can see that the value -2 corresponds to this closed loop where we have the pole at -1, which was the pole that we were trying to check here. Now, keep in mind that this is theta equals 0, and what happens if I do it like -2 and run it again? Then you can see we have again the same amplitude, but with a different sign. Now it is +2, and it becomes 180 degrees. It is on the root locus, and if you use that gain, you will end up in -2. So this is on the positive root locus. You can see that the gain is positive, and otherwise, if it's -1, it's going to be the negative root locus. Now, what happens if I choose a totally different pole here? You can see theta is going to be 18 degrees. The result is 0. It's not on the root locus, and you will have an empty k value here. So that's quite nice to note here, that we can basically toy around with this. And what happens if I want to check out 1.3073 as the objective here? Now, I actually looked it up from the root locus plot, and this was basically almost the point where we crossed the j omega axis here. And you can see that the theta value is almost 180 degrees. And if you implement it as equals, you will not get basically the solution. And it would be very unfortunate if we didn't catch this, because as you can see, the pole is 173. And when we use this here, in order to look up what it really is, what the complex conjugate poles are, we end up being at -0.001 plus 1.7309. So this is actually close enough. And you can see that based on the theta value here. So we should basically include this, but this is technically the same as having this. This minor difference here is not really that important. We can just live with that, because practically we cannot have exactly 1.73. So anyways, we're just going to include it when we do it like this here. Now, there could be one more thing that we need to look at, but I'm not really going to care about that. And that would be the numerator being something else than 1. That could be an issue. And you can see it did change a little bit. And the reason why this could be an issue is that if we look at GS, the numerator being not equal to 1 would end up in a different gain value, because the angle condition, or actually the gain condition here, creates something like plus k, no matter what the numerator is. But if we apply this k, you should actually look for 2k equals gain condition, and then k is going to be the half of that, for example. So you have to take into consideration what the numerator is, or what the system's gain is, basically. But I'm not going to be bothering with that, because I'm just going to leave out numerator here, that being equal to 1. And that's not going to be an issue. I'm not going to look at that and grade it, because that's not that important in my opinion. I just pointed it out here, so that's what matters. You have to know this. If you're applying the gain condition in an exam, you should also check what 1 plus k times g looks like. K times gs equals 0. From PCS, if you derive this, you should look at what the gain value here is. So because you're examining GS on its own, you should take care of the gain of the system. If it's 2, you should look at 2k equals the gain condition. So therefore, if this would have been the case, I would have divided by the numerator's last element or something like that. Yeah. Now, this is basically the solution here, and hope that it was helpful, and hope that you enjoyed the quiz here. The upcoming quizzes might be a little bit more difficult than this one here, but yeah, see you in the next videos.